Good morning. Today we will start with entropy. We will start with entropy generation associated with the heat transfer. Take example of this container which contains water and the temperature inside is 100 degrees Celsius, and this container will lose 600 kilojoule heat to the surrounding temperature is 25. When it loses, the water will start to condense. A frictional piston cylinder device contains a saturated liquid vapor mixture at 100 degrees Celsius. During a constant pressure process, 600 kilojoule of heat is transferred to the surrounding air at 25 degrees Celsius. As a result, part of the water vapor contained in the cylinder condense. Find the entropy change of water and the total entropy generation during this heat transfer process. So there are no reversibilities involved within the system boundaries, and thus the process is internally reversible. The water temperature remains constant at 100 degrees Celsius everywhere, including the boundaries. So we must take the water in the cylinder as a system. This is closed system. Since no mass crosses the system boundary during the process, we note that the pressure and the temperature of the water in the cylinder remains constant during the process. So also the entropy of system decreases during the process because of heat loss. So system entropy will decrease and your surrounding entropy will increase. Noting that the water undergoes an internally reversible isothermal process, its entropy change can be determined from, because heat is transferred at constant temperature, so entropy, you can say, of the system will decrease. It can be find from this 600 kilojoule loss, which is negative, divided by this total value 100 plus 273, which is minus 161. Now this is the entropy loss of the system. Now to determine the total entropy generation during this process, we consider the extended surface, which includes the water, the piston cylinder device and the region immediately outside the system. Means now we will consider the outer surrounding, which is your piston boundary here, this piston and the surrounding. The entropy balance for this extended system is equal to system plus immediate surrounding, which is S in, S out. S out we had S in minus S out plus S generation is equal to delta S of the system. Now we know if you have to measure the entropy gained by the surrounding, which is Q out by TV. TV is the boundary temperature, which is 25 degrees Celsius, plus S generation is equal to del S system. So S generation is equal to Q out by TB plus del S system. Del S system we had already calculated, which is minus 1.61. Q out is 600. Heat transferred to the surrounding is 600. Taken by surrounding is 600. And temperature of the surrounding, means including your surrounding, is 25. So you had S generation is equal to 0.40. So the entropy generation in this case is entirely due to the irreversible heat transfer through a finite temperature difference. Note that entropy change of this extended system is equivalent to the entropy change of water, since the piston cylinder device and the immediate surrounding do not experience any change of state at any point, and thus any change in property including entropy. We can also discuss a special case where entropy generation is 0. So your entropy generation will be 0 when there is a heat transfer across a, you can say, very small temperature difference. Let us consider the case where the surrounding air temperature is differential amount below 100 degrees Celsius, say 99.99 instead of being 25. This time heat transfer from the saturated water to the surrounding air will take place through a differential temperature difference, rendering this process reversible. So it can be shown S generation is equal to 0 for this process. So in example, it is determined that 0.4 kilojoule per kilogram of entropy is generated during the heat transfer process, but it is not clear where exactly the entropy generation takes place and how. To pinpoint the location of entropy generation, we need to be more precise about the description of the system, its surrounding and the system boundary. In that example, we assume both the system and surrounding air to be isothermal at 100 and 25 degrees Celsius respectively. This assumption is easily if both fluids are well mixed. The inner surface of the wall must also be at 100 while the outer is 25. Since two bodies in physical contact must have the same temperature at the point of contact, considering that entropy transfer with heat transfer Q through a surface at constant temperature T is Q by T. The entropy transfer from the water into the wall is Q by T system is equal to 1.61. Likewise, the entropy transfer from the outer surface of the wall into the surrounding air is 2 kilojoule. Obviously, entropy is in the amount of 4.4 is generated in the wall. So it means from outer air surrounding this 2 kilojoule of per kilogram heat, you can say entropy is transferred, while from the inside minus 1.6 kilojoule per kilogram of heat is transferred to the surrounding. So net generation is 0.4. Definitely this generation happens within the wall. So we have to identify the location of entropy generation, and this entropy generation location enables us to determine whether a process is internally reversible. So this process verb 721 is internally reversible if the inner surface of wall is taken as system boundary. And does the system exclude the container wall? If the system boundary is taken to be the outer surface of the container wall, then the process is no longer internally reversible, since the wall, which is the site of entropy generation, is not part of the system. For thin wall, it is very tempting to ignore the mass of the wall and to regard the wall as boundary between the system and surrounding. This seemingly harmless choice hides the site of entropy generation. Means if we ignore the wall, we don't know where entropy actually generated is from the view, and is a source of confusion also. The temperature in this case drops suddenly from T system to surrounding. You can say if you ignore the wall, the temperature from system to surrounding drops suddenly at the boundary surface, and confusion arises as to which temperature to use in location of Q by T for entropy transfer at the boundary. Note that if the system and surrounding air are not isothermal as a result of insufficient mixing, then part of entropy generation will occur in both system and surrounding air in the vicinity of the wall. This you can say figure shows the entropy generation during a heat transfer process through a finite temperature difference. So this is when you had ignored the wall is ignored. This is the case when you consider the wall, and this is the case the wall as well the variation of temperature in the system and the surrounding air are considered, means you will consider, because it is not possible that near to the wall temperature will be as the system. Definitely this is the wall temperature, this is the system temperature, and near to the wall there must be some temperature, finite temperature difference, and definitely this is the wall temperature, this is surrounding temperature. So suddenly temperature can't change, so there is a some way gradually temperature change. So this and this is the difference of the temperature between wall and the surrounding, which is also a finite temperature difference. So these points are, you can say, source of entropy generation. Entropy will generate here in the wall and here where you had finite temperature difference. So in this case we had ignored this temperature difference, or you can say temperature change near to the wall and surrounding. So whatever entropy generation, that is only within the wall due to finite temperature difference. Wherever in this case we had ignored the wall thickness, so there is a sudden temperature drop. So definitely whole entropy change will occur at this you can say very thin, which is very thin wall, you can say very small portion, the whole entropy change will occur here. So S generation in both the three cases is same, but we have to find at where this will happen. So in the first case it is clearly visible, in three cases heat transfer is same. So in the first case the whole entropy generation is within the very thin wall, which is not so the cases. So next is when we have taken the wall, the whole entropy generation is within the wall. Now you are very well know that what temperature take at this surface. This you can take the temperature of this wall. If you have to calculate entropy generation at this surface, you have to take this temperature, and during this wall you have to take whatever the temperature at this location to calculate this relation to calculate the entropy generation. So in the third case you can clearly visible that entropy generation is from this point to this point, which is the actual case in the most of cases. So this is up to here about the entropy generation in a wall. Subscribe this channel, like this video. Thank you for watching this video. In the next video come up with the next topic.